Hey, Blake Merritt here, Core Bioag. Today we have Zach Wright here from Living Soils Compost Lab, looking to do some experiments and brought in an expert to kind of guide us along the way. I'll let Zach introduce himself.
So I'm Zach Wright. I'm the director of the Living Soil Compost Lab in Canton, South Dakota. We specialize in microscopy. We specialize in humus analysis. We also look at some more traditional soil and compost metrics. We're essentially educators. So we help farmers and producers of all walks create more of a closed loop fertility system. So a lot of education is involved with that, kind of value adding and identifying and then value adding our waste streams and creating that living component back into our system so that we're not just growing plants, but we're growing everything. And when we're growing everything, we're essentially growing our soil. And when we're growing our soil, we're growing time. We're growing more harvests when we're looking after our soil. So it is my pleasure to be here. I have had the good fortune in a lot of the farms and producers that I've worked with across the country to work with this very extractor. So I've seen it perform. I've gotten a lot of feedback from the growers that are using it, all very positive, and it's my pleasure to be connected here and help Blake and Core Bio conduct an experiment where we're looking at different food resources with our living component, our culture.
Yeah, thanks for the intro, Zach. So yeah, to kind of draw on some of his experience in all of this and kind of taking that to what Core Bioag is trying to do for its customers and increase biological activity, help them implement these practices on their farm, be productive, be efficient at doing it. We wanted to see firsthand what it is that we're doing and what we're trying to achieve. Been a lot of talk on sugar, molasses, feeding biology, getting that carbon out there, building bricks. And so we wanted to kind of put some of that to the test to see feeding sugar, feeding molasses with biology, how effective is that? What type of results can we see with that? And is it an effective way of handling biology, specifically in the starter type mixes when we really have that chance to get as much diversity into the soil as we can? We want to take advantage of that. We're going to put that to the test against some of the products that Core Bioag represents and sells and kind of put a mix together as what we have our customers out there running and kind of let Zach's eyes take a look at that under the microscope and see what he comes up with and get some results for you. So Zach, before we get started with our experiment, I think you've probably done this a few times.
Yeah.
Running sugar, molasses, feeding biology, running different biostimulants. Is that something that you're kind of familiar with?
Absolutely.
Past experiments, what have you seen? Sugar consumption, molasses consumption, feeding biology. We can start there. What have you seen with that type of experiment?
So we have a living component, right? That's our compost, and then we have the extractor, and that's how we're washing that. What we want to do is we also want to, what I call, send them out with groceries. So we want to put things that feed them, but also that feed the plant. And so there are different biostims out there, there are different food resources out there that can actually do both. They can feed your soil essentially and your plant. And so by doing so, we, as a microscopist and as a person that's on farm a lot, advising growers in the season, you know, with their seed treatments, with their in-furrow mixes, with their foliar applications, where they're incorporating biology, what I get to do is I get to look at it up really close. And so from that vantage point over the years, I've been able to see what certain foods do to that really diverse culture. And when I say diverse culture, we're essentially looking at oftentimes the bottom 3-4 rungs of the food chain. Because molasses has been a very good carbon source to put with our non-carbon commercial fertilizers, it's one that's readily available. It's one that a lot of, I would say, more progressive producers have turned to as a amendment to add into their program. So they'll add it with their commercial fertilizers, they'll add it with their biologicals, they'll add it to their insecticides, they'll add it to their, just kind of into the tank. It's a sugar resource, and so that sugar resource should create a response in the plant. Oftentimes what I've seen is when molasses is kind of the sole food resource for that, with that living component, that culture, that extract culture, oftentimes the molasses feeds strictly the bacteria. And when that happens, your bacteria consume all of those sugars. And what happens with that is you end up engaging the bacteria component and just the specific types of bacteria in that culture that like that food resource. In doing so, those bacteria reproduce faster than any other life form that we know of. They say every 15 to 20 minutes, one bacteria becomes two. So in 24 hours, that one bacteria has essentially become 10 million bacteria. So what happens when that culture, that diverse culture of bacteria, fungi, protozoa, nematodes, microarthropods, when that diverse culture is given a very specific food resource, like molasses or any type of sugar essentially, you are essentially feeding the bacteria. And because bacteria grow so fast, they end up using all of the oxygen up in that solution. And when they use all the oxygen up in that solution, they end up cutting off the air supply to a lot of our other living organisms, unfortunately, our second, third rung of the food chain type organisms. So what I have observed over the years is where we have strictly a bacteria, well, we have strictly a sugar resource, a sugar food that's going in with our culture material. We got to use it up really quickly. And if we don't use it up quickly, and I mean less than 8 hours quickly, we see those bacteria completely consume the rest of the culture. They reign supreme. They reproduce faster than anything, and in doing so, they use up all the oxygen, and before you know it, your protozoa, they're gone. The anaerobic protozoa then wake up. Your fungi can be gone. The bacteria have used up all the air that they've then essentially consumed the fungal hypha itself. Spores are a little different. Spores can make it through that. But I've even observed things where, so oftentimes guys will break down or they won't get everything used up by that previous evening. And so they have so much left in their tank that then the following morning when we go out, we pull a sample from the tank, the sprayer, the planter, we analyze that again and we compare it to our metrics from the previous evening, for example. So where that tank has sat for sometimes 8 to 10 hours, the culture, the result of what we have cultured inside of our spray tank is completely different from what we started with. And that can even go as far as the pH is very different. I've seen pHs go up 1 to 1.5 points higher, so more alkaline, just because we did not have any sort of fungal food resource into that culture material, into that tank mix. I've also seen electrical conductivity drop several millisiemens, so several units of measure, just because we lost our diversity, we bloomed the bacteria, and essentially we were left with a bacterial soup by that next morning. So it's oftentimes a question that I get asked is what happens if I break down? What am I going to do with this material? Well, we'll get into that, I guess, the further we go down this hole and we conduct our experiment. And hopefully it will help us shed some light so I can help elaborate more of what happens in the tank because of that. I guess as a teaser, and it's just kind of general advice, we try to keep our living culture and our foods, our groceries, essentially separate. And we put those together per tank. That way, if we do have a breakdown, if we do for some reason have some left over, we're only losing a sprayer tank and not a nurse trailer that's full of already mixed materials. So, but that's sugar and molasses. So that's where what I think we're trying to explore here is what are some of the other food resources we can incorporate that maybe give us a longer shelf life.
Yeah, that's really good information. That's a lot of information to unpack there. I've got a lot of questions about some of it, but let's start really with what we're trying to explore here. We don't want to throw sugar molasses under the bus. I think
Not at all.
Carbon is important. I think there's a time for it, time to use it. You talked about different levels of this food chain or this biological food web. When we're creating a starter mix and we're going to put a seed in the ground and we want to provide the most biology we can, the most diverse biology we can at that time. What's your goal when you're assessing that situation and you're going to help somebody put together this mix? What do you want to create in your mix that you can see in a microscope, these different levels that you talk about, and putting this mix together? What, from your experience, what do you want to see in that mix? What's your goal when you want to put that seed in the ground, and what type of biology do you want out there?
Everything. So I really look at this microbial world as sort of primordial intelligence. You know, these creatures have a specific function in the system, and we see from metagenomic analysis of some of these compost cultures that people are watching a video on YouTube how to make, or they're purchasing from places that distribute such compost cultures that are full of this ecology. You know, we're seeing in upwards of 500 to 1,000 kinds of bacteria and fungi as well. We're seeing such a diversity of species. So I, in my career, have leaned more toward the compost extract world than the compost tea world. And so the goal of an extract is essentially washing that material into a solution so that we can capture the full diversity of that culture. Then incorporating foods with it, I want to stimulate things like fungi, which, like bacteria, are the other half of the bottom of our food chain. We want to promote a fungal component, as we know that most of our terrestrial plants have an association with fungi, not to mention the digestible function of fungi in our soils. So I want to promote the fungi, and I'm a big protozoa fan. I'm a big fan of the kingdom. So out of the 5 kingdoms of life, there's a kingdom called Protista. These are the organisms that eat the organisms. I call them the coyotes or the foxes in the system. So bacteria, if you could imagine, are your rabbits. And most people's soils, in fact, I have not seen a dead soil yet in my 12-year career, have plenty of rabbits, have plenty of bunnies, but there's nothing necessarily present because of agricultural practices that have not really considered these life forms that we have to look at so closely. These foxes, these coyotes, these predators are missing. And so when I'm creating an extract solution with a grower, I am after literally everything, not only the fungi, but I'm after the things that eat the things. And so when it comes to food resources, I'm looking at things that promote fungi. I'm also looking at micronutrients, the entourage effect. So very similar to this culture of 500 to 1,000, let's just say, organisms that we're trying to embed into the system and let them sort it out. I'm also wanting to create an entourage of nutrients, macronutrients and micronutrients as well, to go out with them, to maybe even signal hormonal function in the organisms, but really give a diverse buffet of life forms and nutrients alike into the system and let the system kind of sort it out, which sounds really general and easy, but there's a growing number of producers out there that I myself work with, Blake works with, that a number of us work with now that are doing just that. They're feeding their plants and their soil simultaneously and giving them everything in terms of a food resource, so everything grows.
So Zach, how long have you been doing this? When did you form Living Soils Compost Lab, and how long have you essentially devoted a lot of your time and efforts into soil biology?
So I was introduced to all this in 2012, and I took over the Living Soil Compost Lab as director in 2013.
Perfect. I'm not a soil biologist, microbiologist, and I'm not going to claim to be one. I've had to really rethink a lot of my approach to soil biology and really learn fast. You've been a great tool for me, a great asset for me as I do that. And we get posed a lot of questions. We're working with growers, boots on the ground, doing soil testing, evaluating that type of stuff, trying to help implement these practices. Just getting your point of view. You know, some of these questions we get, looking at soil tests and nutrient values that are out there, nitrogen, phosphorus, potassium. You know, everybody wants to have a better ROI. Everybody wants to make more money. How does soil biology play a role in that? How does it impact the potential to reduce fertilizer cost and create better soil efficiency, better soil functionality, and where does biology impact that, play a role in it? How can we increase that impact from soil biology, and what type of approaches can growers think about doing?
So I largely look at the soil as a gut. It's kind of the gut of the earth. It's the layer of the earth that should digest. And unfortunately, from what I see from a microscopic point of view, so again, looking very closely at people's actual anchors that they're putting their plants into, I see a constipated system. I see a system that can't digest and function. It's very similar to our own systems and the digestive systems of animals alike. And so from that point of view, and seeing what's there and what's not there, I think that as producers, we really have the opportunity to put back what is missing. And because of that, it's a very simple analogy. Why put the milk out there when you could put the cow? We're putting the factories back into the system, which make nutrients available. These very microorganisms, they eat rocks. They're the lithobionts, which are bacteria that are known for eating rocks. They're literally breaking down the parent material. So by putting these intelligent life forms out into the system, we are essentially re-engaging the digestive function and creating the digestive enzymes via those microbes so that our system can digest and cycle itself again and recycle and upcycle it into more humus formations. And so I talk a lot about humus. It's kind of, to put it very generally speaking, humus is the artifact of soil function. It's how well is our organic matter actually breaking down and repackaging itself into these nice little microaggregates of carbon that will essentially be there for centuries, if not millennia. It takes the microbes to do that. And so in supporting and supplementing the system, even a commercial system that's very NPK heavy, very traditional and conventional in its approach, supplementing the system for starters with a biological component, we have seen a drastic reduction in the macronutrients N, P, and K across the board because our system's functioning again, and we have nutrient cycling happening again, which, I mean, at a micro level, from an ecological standpoint, it's when an organism meets an organism that we start to digest and we start to send those nutrients, which we know at the bottom of the food chain are eating the rocks and actually, you know, accessing the minerals themselves. It takes something to come along and eat that in order to start putting that and sending it up the food chain. And that is what the food web theory is essentially addressing.
No, that's great. Yeah, I think most growers wish that this was kind of a silver bullet approach where I'm going to put this application out here and these microbes are going to start functioning and working. I mean, I'm pretty upfront and honest with them. That's really not how it works. We try to put this in a plan approach, a management system.
Me too.
What can you speak to that? Maybe, you know, in a conventional system, where would be the first place a grower should focus their management practice to when trying to implement soil biology? Is it just a get out there and go approach? You just got to start somewhere, or is there a specific point that a grower should look to?
I would say the get out there and go approach is great because I think it's time that we embrace this new approach, this new mode of action into our growing system. Instead of just growing plants, maybe we grow everything and then the plants ultimately benefit and everything benefits then. I think that the most strategic place that I've seen to start is really on the seed. It's right on the baby. And the analogy I've always used is what would you rather give a newborn baby? Would you rather give a newborn baby a bottle of Monster Bang Energy, or would you rather give it breast milk? And I liken the biological approach and the extract culture, or even a compost tea, but an aerobic compost derived culture, as that breast milk. It acts as that flywheel that helps to make the inherent fertility that's in our soils available again, just by being positioned back in place around that baby seed, where then the biology and the plant grow together into the soil. And so the establishment of a biological early on is strategically the best place that I could say for anybody to start, and then come in with your commercial program. You know, don't throw away your conventional wisdom whatsoever. But I think that there is a strategic place that, like you were saying, that we can initiate this start, and then it becomes a component into our system that doesn't necessarily leach away. So as we put biology in, you know, season after season, year after year, we start to accumulate a biomass of function in our system again. Then it comes down to managing disturbance. And so oftentimes with our larger scale producers, we're managing disturbance at that point.
Yeah. No, that's great, and that really ties back to really what our goal of this video is, and looking at how can we start that seed off at, you know, the best chance possible, and what type of biology we can get with it, and that's what we want to take a look at these samples with, and see what type of benefits each specific culture fed differently can do. But tying back a lot of that, you know, and the NPK side of it, and now the potential for monetization of bushels and the carbon credits, and I think this approach is going to be looked at a lot more by growers, and so I think having a lot of this information out there so that they can kind of digest this and look at how biology can play a specific role in reducing these synthetic inputs, and yeah, with the potential for CI scores and monetization of this to come down the road, it could be pretty impactful for growers. So we got our experiments made. We made a batch of extract from the core compost and added the biostimulants that we're using at core. We use sea crop, we use kelp products, fish products, things like that. So we made our starter mix, and then we're going to put that to the test against sugar, molasses, and see what type of results we come up with. Maybe good, bad, maybe mixed results. We don't know yet, but just looking to be informative and help guys make decisions as to what to do. So let's step over to our lab here. Very scientific over here, but Zach's brought his mobile lab down with them, so we'll see what we come up with.
Okay, so with the assistance of several hundred flies and the farm dog Kimba, I was able to do both of the comparison analysis of the core bio compost mixes with different groceries. So essentially we had, as you were saying earlier, we had the core bio with molasses, and we had the core bio with kind of the core bio mix that you all have created and put together. And without knowing too much about what was in the mix or anything, I was able to do a bioassay directly from the brewer itself. I think you had said that these had been brewing for about 25 hours.
Yeah, how long they were sitting. Mm-hmm. Yeah, they were sitting for, at least 24 hours.
Okay.
Yeah.
Okay. So other than an hour between the two, the first one that I did the assay on, so I did a live assay here on the microscope, just took a direct drop from the solution itself, which are in both of those pictures there. So it was a 1-to-1 dilution, essentially. There was no diluting to it. It was the core compost and what we called the molasses, kind of the industry standard. And so going through this, to start at the top, we had a total fungal to bacterial ratio of 2 to 31. So again, that first number is fungi, second number is bacteria. So we were at about a 1 to 15 F to B ratio. So for starters, I would say that we have a bacterially dominated culture, clearly by looking at the relationship between fungi and bacteria. We look at that because it's the bottom of the food chain. Typically what I see in ag soils and production soils, conventional and organic alike, as a soil testing lab, we do a lot of these for people's soils, and we see anywhere between 1 to 100 fungi to bacteria to up. I mean, we have some that are 1 to 10,000. 10,000 times the biomass of bacteria than fungi. So very skewed in terms of the bottom of the food chain. And what we know from a soil food web theory, that is that our crops and the things that we're trying to grow really do need a stronger fungal component. Some even say an equal 1-to-1 fungi to bacterial ratio is kind of the goal. I just use this to I use the fungal to bacterial ratio to kind of track it. So back to the extract that was made with the molasses, over 24 hours, it's now sat together. So the foods and the culture have been together. We had a 2 to 31 fungal to bacterial ratio. As I moved down the assay, we found no nematodes, good or bad, in the solution. So that was probably attributed to the culture that we started with, not having the nematodes to begin with. But sometimes it's worth looking further at the extract without any foods to see if maybe the nematodes were there, but something we put in eliminated them.
How often do you see nematodes in a solution or in a compost? Well, like in a compost and then extracted and in a solution.
So in a compost, it depends on the age of the material. So some people make composts thermophilically. They use heat and they turn it, and it's a lot less mature of a product, and there's higher nematodes because of that. Oftentimes, we look at a lot of Johnson-Su bioreactors, which is a 12 greater than or equal to 12-month culture typically by the time we see it, because it's a static method. And that has, by that time, through the maturation process of the compost, the nematode populations kind of decrease over time. We like to say that the nematodes go to the bottom of the pile. But either way, nematodes we often find in our extracts, especially using the Core Bio extractor. I have personally verified many mixes that have been made on the farm doing this kind of very similar experiment where we have nematodes in solution. So that's good for me as an advisor to these growers, because I want to, again, see everything go out into the system. I don't want something that, because of the filters or the plumbing or the pump itself, that's eliminating any of that diversity. So I do find them oftentimes through the use of this very extractor. I just didn't find them here with the molasses.
Yeah, I think that's a good point. I mean, we like to utilize our extractor, and it's good to see that we can get those materials out of the machine. And it also plays to the part, I mean, I really try to harp on guys to make their own compost, and I think that's going to be a valuable tool for them. A lot of guys, they don't want to get into it, but that's where the value that they can see on their own farm by making their own material. Maybe they need to cut that with some outside sources, get more diversity in there, but being able to, like you say, make their own compost, whether it's Johnson-Su or whatnot, and be able to achieve those nematode numbers and then see that come out the extractor. That's really that's important information.
Yeah, it's a valuable tool, and there's a lot of systems that I've seen that have been more DIY, where they've tried to make their own sort of extractor or induction tank that they can wash their compost with. And lo and behold, we were eliminating not only our nematodes, but our protozoa. So the system was too aggressive that we were losing all that diversity because we were finding it in the filter.
I'll ask you a couple of questions that I get posed a lot. Running biology through pumps. What effect have you seen? Obviously, we have pumps on our extractor, so it's obviously running through a pump, maybe several times. What's the downside? What type of knowledge can you present on that topic, that question that we get posed quite a bit?
I think the main thing to look at is PSI. Look at the pressure that's inside the system. And as long as we stay well under 80 PSI, and that's a conservative low number that I oftentimes, you know, tell people, but as long as we keep our PSI low enough, we generally speaking see the organism transfer. So what I like to do is I like to look at the compost material at first, and I'll, in a test tube, in a 50 ml test tube, we'll figure out the rate that they're going to be applying it, and we'll make a dilution so we can kind of see what is that full expanse of that culture here. Then we'll put it through the system, and then we'll relook at it. And oftentimes we see just things are just shredded, especially with things that are big, like nematodes, for example. You'll just see them ripped in half. So there are higher speed impeller pumps that I've seen from time to time, or trash pumps. Trash pumps are they vary greatly. Oftentimes in like a DIY system, a trash pump's used, and we'll see all these just shredded nematodes after it's gone through the extraction process. And so I think it's very important for producers that are getting into this to really go the extra step and do the verification. And it's as simple as taking on microscopy. So as a lab, we do train a lot of growers how to use microscopes. We have been positioned very well to look at a lot of people's Johnson Su bioreactors. So a lot of people watch the YouTube video, they watch Jay Young, Red Young Angus, or they watch Dr. Johnson himself perform this. And there's a lot of people on YouTube that are making these cultures, but then they don't know what they made. And so they find out about us, and we help them verify just in the similar way that we looked at this today to explain to them what they've made. And I can say by and large, most people that are following those instructions are doing a great job. And with that, you have the power of creating what I would say is one of the best biologicals that you can obviously put on your farm because it's of your farm.
Yeah, we really try to preach that with a lot of our growers. And you think about the life cycle of a microbe. It's coming from compost, and then you extract it. So it's going through an extractor, and probably going to go into a nurse tank and maybe get recirculated, and then into a sprayer or a planter, and finally out into the field. It gets moved around a lot, but if we can first see that we're getting the material, and then how we can preserve it based on some of the information we know, those can be really valuable tools.
Definitely. So without further ado, the core bio culture with the sugar food resource had a fungal to bacterial ratio of 2 to 31. So that's saying that there's over 15 times more bacterial biomass in that than there is fungi. Bacteria, fungi, bottom of the food chain. We'd like to put those two in proportion to one another because we are trying to achieve a more narrow proportion of fungi to bacteria for our row crops. Moving down the assay, we didn't find any nematodes at all. Then moving down further, we look at the next table, which are the protozoa. So I like to call these the second rung of the food chain, the second trophic level of life. These are the foxes and the coyotes. These are the things that eat the rabbits, the bacteria, essentially. And with this mixture, we did have all three groups of protozoa present. So we had flagellates present, we had amoeba present, which are both the aerobic protozoa that we would like to see. And then we also had a number of ciliates present as well, which are more of an indicator species. The ciliate protozoa isn't a bad parasitic organism necessarily or a pathogen, but what it does indicate is that our solution is running out of air. And what we are always trying to achieve with what we're putting out in the system is air. We want oxygen. We want an aerobic culture going out into our crop systems, which is an aerobic growing system. So we're always trying to promote as much air as possible. So with the presence of the ciliates, I'm not really that concerned because our most dominant protozoa group in the core bio and sugar mixture was the amoeba. And amoeba are great. Amoeba eat bacteria. Some amoeba are so big they eat in upwards of 10,000 bacteria a day. That's a lot of nutrients that those things are cycling up the food chain and making little tiny micro casts of manure, essentially, which are plant available forms of food.
The flagellates as well, we had a good flagellate presence. So far, I would say that not only can we assure that our extractor is not harming the protozoa, because like I said earlier, some people's homemade projects are completely decimating their protozoa component because of the aggressiveness of whether it's their pump or their pressure or just their screens are too small. So we can see that we have organism transfer. We can also see so far that we have a culture, a quality of health to the culture. Typically in very toxic and very disturbed environments from a soil level, the protozoa are completely gone. They are completely gone. And as a lab methodology, we incubate our soil samples, so we give the sample time to saturate, to wake everything up. Oftentimes we look at soils and the protozoa, the second rung of the food chain, is gone. And it's truly the gap in the growing system. So already I can tell from the Core Bio compost mix that we have a quality of health to that culture. Then moving down to the next table, we look at actinobacteria, oomycetes. And the oomycetes are your fancy word for water molds. So typically speaking, our most pathogenic funguses in our soils and in our growing systems are water mold-like funguses, and they have a very distinct look to them in the microscope. So we had a presence of water mold fungus in that mixture, but a very low presence. Actinobacteria as well, we had a little bit of actinobacteria. Actinobacteria are actually very good forms of bacteria, but they do indicate that we are running out of air. So what I'm already able to distinguish by just moving down this assay in review is that the sugar is basically, it does have a anaerobic, there is an anaerobic quality to this culture by the presence of not only the oomycetes, the actinobacteria, as well as the ciliate protozoa. So then we get to our bottom table on this first analysis where we have bacteria and fungi. So bacteria, we're at roughly a little over 1,500 micrograms per gram for biomass. Fungi was roughly almost 100 micrograms per gram. So from an extract solution, from a liquid solution, just taken directly out of the tank like this is both very good in my opinion. The bacteria is obviously a little high, but in terms of the expected range of bacteria for any sort of healthy culture system, we want to be between 300 and 3,000 micrograms. So we're right smack dab in the middle. So nothing egregious, but oftentimes what I've seen from an extract where we're using sugar as the food resources is, especially over time, that bacteria biomass goes up. So we lose shelf life is what I would call it. So all things considered in this first analysis, the presence of the ciliates, the oomycetes component is lower than the good fungi component, so I'm not concerned there. But with the ciliates present, with the actinobacteria present, I would say that you would want to get this applied pretty soon, within probably 6 hours.
So obviously taking this sugar extract solution, putting this into the soil as the sole food source, obviously it's going to have things to feed on in the soil when it gets there. Is there a huge expectancy of continued growth, or is there some direction that you think this extract may be going as it enters the soil?
As it enters the soil, it's going to be going into an aerobic environment, hopefully. And so it's going to buffer the bacterial growth the second it gets out of the sprayer and into that aerobic system. The longer it sits in the tank, it's going to run out of air. Mm-hmm. And your bacteria are going to continue to grow. If we were to look at this 12 hours later, I would venture to guess that biomass of bacteria is going to be way higher, your fungi is going to be lower, and we're going to see your beneficial protozoa start to diminish because they're going to also run out of air and the ciliates are going to start growing. So out in the soil, sugar is kind of a limited feedstock that it's going to promote bacteria. Bacteria are literally in every soil. They are everywhere. It's the fungal component that we want to promote. And so in looking at different food resources in an extract sort of system, I tend to favor more of a food resource that feeds the fungal component more over the
food resource that feeds the bacterial component. Again, because we're trying to establish through our extract and promote through the foods in our extract that fungal component back into our soils, which are overall very skewed in most production growing systems.
Yeah, it would make sense if we're going to take the time to make it and put it out there, we want to put out as little as possible bacteria as we can, as we're probably already dominant in that aspect of it in the soil.
Very much so. Very much so. So moving now to the core bio mix with the core bioculture with the core biofoods mix, where we have substituted the sugar as our food for, as you had mentioned earlier, sea crop.
Yep, sea crop, kelp, and we do some liquid fish.
Kelp
yeah.
and liquid fish.
That's what we used in this specific example, yeah.
We have a total fungal to bacterial ratio in the first table of 4 to 35. So in comparison to our last sample, we had a 2 to 31 fungal to bacterial ratio. Here we have a 4 to 35, so a much narrower fungal to bacterial ratio. Just looking and comparing those two tables alone, I like the way this one looks because we don't have such a dominant bacterial biomass. So as I move down into the tables, again, we did not find nematodes in this culture, which leads me to think that we probably didn't have nematodes to start with, which is okay, because I've now looked at both of these. I can say both of these had a very high fungal component. Both of these solutions, very high fungal spore component specifically, as well as active fungi, which tells me there is a maturity to the compost material that you're using, which is fantastic. We want especially spores because they are encapsulated and they sort of make it through all of the fine screens and into the system, I would argue better than an active fungal hypha. So as I move down the list, again, no nematodes, just like the last sample. When we look at the protozoa in the next table, we did not find any flagellates. We found a predominant amoeba component, which is excellent. Again, foxes and coyotes, we want the predators in the system. What was different was we didn't have any ciliates in this. So without using a dissolved oxygen meter, I can tell that this is a more aerobic culture, just because we went from having ciliates to having no ciliates in this one. Moving down again into the next table, we had 0 actinobacteria. Another good sign that the material is aerobic, as actinos start to show up when we start to run out of air. Oomycetes, again, they're about the same as the last sample, slightly less, I believe. Yes, slightly less in biomass. Again, that's your water mold fungus, also an indicator of low oxygen environments. Also, it's just very natural for oomycetes to be in a compost culture, especially if it's somewhat moist when it's the way it's stored. Moving down to the last table, the bacteria and fungal table, here we see a much lower, almost a half of the biomass of bacteria in this mixture versus the mixture that had the sugar. The fungal biomass was at 85. Our last sample was at somewhere in the low 90s, so fungi activity was about the same. And again, we're only looking at the active fungi in that part of the table. We're not looking at the spores. Both cultures, both solutions, great fungal spore component, and that is exactly what we want to see to represent our fungi. Overall, comparing the two, very good compost culture to start with, good humus. I saw a lot of fulvics and humics in there, even saw some humin, which is the insoluble humus substance. That could either be because of the age of the compost, that could also be because of added biochar or linardite, humates, that type of component. Oftentimes people blend that in with their composts. But if I had to pick one or the other, without knowing the ingredients component, I would have to say I would pick the core bio with the mixture of foods, simply because we don't see the same level of anaerobic indicators and we see a lot less of a bacterial biomass. And to me, that speaks shelf stability. So if we do break down today, we are not going to run out of air as quickly as the other one is, to where by the time we get up and running again, at that point, the culture is completely changed and we're spraying a bacterial soup versus this diverse, beautiful culture of really a whole ecosystem of life. Definitely. But in comparison of both of them were excellent. If I was on a farm and this is what we were working with, either one of these, I would be happy because we saw the diversity transferred.
As biology becomes more important and people and farmers and growers and producers management practices, limiting NPK fertilizers, no-till cover crop, all the different things that growers have the opportunity to adjust or change or try to implement in their practices. Biology plays a critical role in that. So we wanted to make this video informative, help you guys make those decisions, show you what we're doing and how we can impact those decisions. If you have questions, contact Core BioAg. Contact Zach Wright, Living Soils Compost Lab in Sioux Falls. He can do a lot of different testing. I can kind of let him explain some of the stuff he can do at his lab.
We specialize in bioanalysis, so we are looking using a microscope. We are directly looking up close at your system, be it your soils, be it composts. We do look at manures, just to evaluate the health of the system up very, very close. And we also do a humus analysis in-house, and then we also working with affiliated labs with across the country. So yeah, we're happy to help. livingsoil.net directly links to me. So yeah, happy to help.
Perfect. Thanks for watching.
Thank you.